Hi everyone, this is week 14, which is the last week of the semester. The topic of this week is improper integrals. Before we start solving problems in our template, I want to show you some diagram that we covered in lecture notes. Look at this diagram, please. We can divide improper integrals into two groups, type 1 and type 2. Type 1 consists of improper integrals like this one, and the property here is that the interval of the integration is infinite. Okay, type 1 is all about the integrals whose interval is infinite. And remember what type 2 is. In type 2, we are dealing with the improper integrals, which has this fx is not continuous in the given interval of integration. Okay, here the interval is finite, but the function has discontinuities over this interval. In type 1, the function, there is no problem about the continuity of the function, but the interval is infinite, okay? So let me explain in more details what to do about these two types of improper integrals by solving the problems in our problem solving template. Okay, let's start with the first one here. 24. Here we have an integral whose interval is infinite, right? So this is, let me write first. So this is an type 1 improper integral, right? First of all, we need to divide this integral into two parts like that, from minus infinity to 0 and from 0 to infinity. Okay, then we can deal with separately these two integrals. Look at the intervals, please. You see both intervals are infinite. Intervals are infinite. So this is an improper integral of type 1. Okay, let me write improper integral of type 1. So how to deal with them? We need to put some limits, right? As you remember from the lecture notes, improper integrals are evaluated as limits. So first integral, you need to put some variable here. Let's say, for example, a, write your function. And then what you should do is you need to send that variable to infinity to make, to obtain the very same integral, not to change the question, right? A should be sent to infinity. And similarly for the second integral, you need to name this infinity part as a variable. Let's put b. And then to obtain this, to have the same question, you need to send b to infinity. Sorry, here a should be sent to minus infinity, of course. Okay, Ra goes to minus infinity. Okay, so let me emphasize what I did with the variables. So, this instead of this this infinity, I put b. Then what I did was I sent b to infinity. Okay, now as we have finite definite integrals inside the parentheses of limits, and we can evaluate them. Okay, how do you evaluate this integral? We will use substitution to evaluate such integrals. 2x e to the power minus x squared dx. Let's choose u as x squared, okay? And then du becomes 2x dx. Then this integral can be rewritten as this part, 2x dx is exactly du, right? And we choose this part as u. That's why it is e to the power minus u du. And this integral is evaluated as e to the power minus u divided by minus 1. This is how you should evaluate it. So let's write this down. Here what we have, a goes to minus infinity, and we evaluated the integral. And then of course you need to do back substitution. For you need to turn back to x. So this integral is evaluated as a to the power minus x squared divided by minus 1, evaluated at upper level boundaries like that. And similarly for the second one, e to the power minus x squared divided by minus 1, then b is from, x is from 0 to b. Okay, then time to insert boundaries, of course. Limit as a goes to minus infinity. If you insert 0, you will obtain minus 1. Minus, if you insert a, there is another minus coming from here, so e to the power minus a squared. And similarly for the second one, it is e to the power minus b squared, right? Plus 1, because minus 1, but you have an extra minus there, plus 1. Now it's time to compute the limits, of course. Let me write this down again. E goes to minus infinity, minus 1 plus 1 over e to the power a squared. And this is b goes to infinity, 1 over b to the minus 1 over b to the power b squared, e to the power b squared plus 1. Okay, time to compute the limits. If a goes to minus infinity, maybe it was not a good idea to write this as a ratio. Maybe it should be like that, okay? If a goes to minus infinity, okay, it doesn't matter how to write it, the result won't change. Okay, let me give this notation. If a goes to minus infinity, a squared is plus infinite, right? And then this part will go to 0. Similarly, if b goes to infinity, the denominator here goes to infinity. So this part also goes to 0. Then what do we have as the result? We have minus 1 coming from the first limit and plus 1 coming from here. But there is a minus sign in between. So the result is let me see. By the way, I think I forgot to put this sign as a plus because we are dividing the integral, you know, these are all should be pluses. So the result is 0, which is a finite number. That's why if the result, that's why we will call this improper integral as convergent. If the result of the limits of your improper integral are finite, you will call your improper integral as convergent. Integral is convergent, okay? So let's continue with the next example then. Now we can deal with this one, 25. It is this question from 0 to 1, x ln x dx. Now, there is no problem about the being infinite of the interval. We have a finite, very nice finite interval. But the problem is the function inside your integral, which is this function x times ln x, is not continuous over this interval, is not continuous. At which point, you know, let me remind you the graph of ln x function. This function is not continuous at 0, as you can see it. When x goes to 0, ln x diverges to minus infinity. That's why ln x is not continuous at 0, so f of x is not continuous at the point 0, which is the lower boundary of your integral. Such integrals are still called improper, and this is an improper integral of type 2 now. We have an improper integral of type 2 here. How to deal with improper integrals of type 2? So you first detect the problem. Your function has a problem at this lower boundary. Then to fix that problem, you need to put a variable there, okay? To fix the problem, just name that part as a variable. And then you need to send that variable to where it should be. It should be approaching to 0, but from which direction? Let me explain. Always you let your variable to approach to the point lower or upper boundary inside the interval. And here, if a is inside the interval 0, 1, the direction should be from right? Okay, this is how you handle that integral. Then time to evaluate the definite integral inside, which has no problems. This is now a formal definite integral for us. And this integral should be evaluated by using integration by parts, okay? How do you apply integration by parts? You need to solve, okay, remember our shortcut lab there. Which shortcut comes first should be chosen as you. Let me remind you what is this shortcut. L stands for logarithm functions, A stands for arctangent, arcsine inverse trigonometric functions, P represents polynomial, T means trigonometric, E means exponential function. So whichever comes first, you need to choose that function as your U. So this part should be chosen as U, and the remaining part should be chosen as dv, right? Okay, let's construct the diagram that will give us the integration by parts. So we choose u and we choose dv. U is ln x, dv is x dx. Then what is du? Derivative of ln x is 1 over x dx. And from dv to v, you can pass by taking integral, of course. Then it is x squared over 2. And the formula for integration by parts goes in this direction. You first multiply u and v, so it goes like ln x times x squared minus 2. Then integral of v times du, so it is x squared over 2, 1 over x dx. And all those things are happening inside this limit, right? You got to put your limit. By the way, since this is a definite integral, you should also put boundaries here, where x runs from a to 1, okay? Then you can continue computing this line. We have limit, a goes to 0 from right. Okay, now time to insert. It is ln 1. I am first inserting 1 for x. ln 1 is 0, so nothing comes from the upper bound. Now insert a for x. A squared over 2. There should be a minus in front. What kind of integral you have here? This is a to 1. If you do the simplification, it is just x dx, right? So minus, this is 1 over 2 x squared over 2 from x equals 8 to x equals 1. Okay, let's insert the boundaries here too. If you insert 1, don't forget to put minus sign. If you insert 1, what you obtain, you have 1 over 4. Minus, now you need to insert a squared over 4, right? This is what you have. And then if you want to get rid of this parenthesis, you can by changing the signs like that. Okay, now time to take the limit. If a goes to 0 from right, this part goes to minus infinity, and this part goes to 0. So, by the way, this is directly 0 in the limiting case, but here you have an indeterminate form, right? 0 times plus or minus infinite is an indeterminate form. How do we get rid of that indeterminate form? Let's deal with that limit separately here. Limit let me take this, okay, let me write this down again. Limit ln a square over 2. This is an indeterminate form like that. So it is evaluated like you can take one of the functions to the denominator by taking the reciprocal of it. Then what happens? Now this is still an indeterminate form, minus infinity over infinity, but to this type of form you can directly apply L'Hopital's rule. That's why we are transforming this indeterminate form, this product, to this ratio, to which we can apply L'Hopital's rule directly. So let's apply it. L'Hopital's rule. Okay. L'Hopital's rule is applied how? You take the derivative of the denominator and then you take the derivative of the denominator separately. This is the, it should be cube, of course. This is the derivative of the denominator. So what we have, after you do the simplifications, you have just this expression. So this limit is obviously 0. That's how we handle such indeterminate forms by applying L'Hopital's rule. So this becomes 0, and here is the detailed computation for that part. Then finally, we can give the result as, I guess, just minus 1 over 4, which shows, okay, let me say this is a finite number, so the given improper integral is convergent. Improper integral is a convergent one, okay? If the result of the limit would be infinite, I would say the improper integral is divergent, right? Okay, let's move on. Let me also invent here one more example that has an discontinuity at the upper boundary of the, or at the middle point of the given interval. Okay, let's also try this one. From 0 to 2, 1 over 1 minus x squared dx. At first sight, it seems like a very nice normal definite integral, but we have to be careful. Okay, the interval is finite, but this function here has a discontinuity over the given interval. F of x is like that, which is not continuous at x equals 1, which is an insider point of this given interval. So our integral is an improper one. Integral of type 2. Again, how do we deal with them? First of all, since this is a middle point, not the lower bound, not the upper bound, but a middle point, we need to divide the integral, given improper integral, into 2 parts at this point. So from 0 to 1, 1 minus x squared dx plus, from where I left, I continue from 1 to 2, the same integral. Okay, now the problem is all about this point, right? Then I need to name that point as a variable. Okay, now I will name this part as A and this part as B. And I will construct the limits accordingly. So here I should write from 0 to A, where A goes to 1 from the lower direction. So the one-sided limit is like that. I write the integral like this. And the second part is from B to 2. The integral is the same. And then write the limit. You need to send B to 1 from the upper part. So B goes to 1 from the positive direction. I mean, from the bigger direction, like that. Okay, the second limit looks like that. Now, time to evaluate these totally normal definite integrals. Okay, how do we evaluate them? You need to concentrate of this function now. You can decompose the denominator of this function, right? Like this. So we can write a partial fraction decomposition of this rational function. It should be decomposed like this, b over 1 plus x. And then you need to do these expansions to have a common denominator like that. Then what we have, a times x plus 1 plus b times 1 minus x should be just whatever you see on the left-hand side for denominator. And to find out what is a and b, you can just insert the roots. For example, if x is minus 1, this part is gone. So minus 2, if x is minus 1, it is 2b equals 1, so b is 1/2. Similarly, insert the root of this part, and then this part is totally gone, then you obtain 2a equals b, giving you that a equals 1/2. Okay, then the integral is, so the integral, let me write down the integral. The x over 1 minus x squared is evaluated as 1/2 is the value for a, and then another 1/2 for the value of b. These are the integrals now. So how do you evaluate this? You can take this 1/2 out from the integral, then the remaining part is evaluated as minus ln 1 minus x, right? And similarly, this is plus ln of that given function. So for our improper integral, then I should insert this evaluated result into limits. A goes to 1 from left. So this is what we have, right? Minus 1/2 ln 1 minus x. These are absolute signs. Be careful. You need to evaluate. Okay. Dx over x is ln absolute sign of x, as you remember. Okay, so I am directly inserting the result of the integration inside the limits. This is one part of the limit. There is also a similar limit for the second part, right? So limit b goes to 1 from right. I will insert the same thing. So what is it? Minus 2. Like something like this. Okay. Now time to evaluate the limits. By the way, I need to insert from 0 to a for this integral. Okay, let's do that on it. If I insert the lower bound for this integral, which is 0, so ln 1 is 0, this part is gone. ln 1 is 0, this part is gone. So I need to insert a now. So that I will have for x, all the x's as a. Okay, and let's do the same for the second integral. This time we will first insert 2, okay? If I insert 2 here, 1 minus 2 is minus 1, but we hope, thanks God, we have an absolute sign. Here, ln 1 is 0, gone. If I insert 2 here, I will obtain ln 3, so inserting the upper bound, which x equals 2 gives us 1/2 ln 3 minus, now I will insert the lower bound for this integral, which is b. It goes like, I am just inserting b whenever I see x, right? Something like this. Okay, and then if you look into more details about the limits, if I send a to 1 from a smaller direction, what happens here? This part goes to 0. This part goes to 0 from right, so ln 0 from right becomes minus infinity. Also here, if I insert a equals 1, we will have 1 over 2 ln 2. Let's look at the second part. If b goes to 1 from the bigger direction, this part goes to 0. That's why this part goes to minus infinity. If b goes to 1, this part becomes ln 2. So the result of the limits are, there is an extra minus sign here. Minus minus is a plus infinity. This is the result of the first integral. And similarly, we have constant minus minus will make it another plus infinity. So the result of the limits altogether is a plus infinite. So the given improper integral is a convergent one. Okay, so let me show you the question. This was an improper integral which has a discontinuity at the middle point. To deal with that middle point problem, I divided the integral into two parts like that. And then as highlighted in yellow, the problematic parts are named as a variable, and then that variable is sent to the correct number from the correct direction. And then we deal with evaluating the integral, then we deal with how to compute the limits to find out the result. I stop here for the first part, okay?